kind of right there where it starts going up and then right there where it starts leveling off. Just find those 2 points and just take the midpoint of them. That's good enough. So be ready for wimpy equivalence point indications again. I'll get rid of this though. Now what we're going to do with this, we're going to use this to figure out what the Ka1 and Ka2 of the diprotic acid is, or the Ks are. Anybody remember how to take a titration curve and determine a Ka value? Do some homework. And you're going to have to do this in the lab. We had talked about this last week. Let's just take the first hydrogen coming off and get to the equivalence point right here. From this point to that point, we're titrating the first hydrogen off. This is the reaction that's happening, that first one on. You may remember that however much of the base it takes to get to the equivalence point, cut that in half. What do we call that point at which the full amount gets cut in half? What is that pH right there called? Right, it's the halfway point. What do you call that? Halfway point is what it is. Yeah, the halfway point. Now remember that the halfway point is where the pH at that point, which we can read it right on the graph. That's equal to what? The pKa of the acid. What a handy thing that is to know. Now, this is only for pKa1 because we got 2 Kas. So halfway to the first equivalence point is going to give us the pKa1 from this acid. We assume, it's not really true, but we're going to assume when we do this titration that only the first hydrogen comes off all molecules at this point where it's all neutralized. So only the first H's are coming off of molecules at that point. Then once we've hit the equivalence point for that, where all of them have lost their first hydrogen, then molecules start having their second hydrogens taken off. And what I'm saying is this. Look up here. At the end of the first K equivalence point, that's where the second one starts. So you don't go back to the beginning to take halfway between this and there. You just start there and go from the end of the first K to the second K. So from that point to this point is, this first section is Ka1, the second section is Ka2. So this halfway point, I'm just going to estimate it, and I might be off. Right about there is the point at which whatever the pH is here, that's going to be equal to pKa2. But I just want you to know that you don't start at the beginning for Ka2, you start at the end of Ka1 for Ka2. Now that I've mentioned, you remember that about the halfway point and how the pH at that halfway point equals the Ka for the acid, pKa for the acid. So when you're trying to identify an acid, boy, it's really nice to know that. You'd do difficult math if you had to just use math to solve for that. That's it. That's the new things. That's everything in the buffer chapter. So our quiz, assuming that we have school every day, is going to be next Thursday. If we don't have school, maybe we'll just push that back to Friday. Okay? Now, with 20 or so minutes left, maybe 25 minutes, I'm going to ask you to try 2 sample problems. This is the first. I'm saving the most difficult one for the last. This one shouldn't be bad. Feel free to work through this with somebody else, kind of talk it out. I don't mind that at all. In fact, I encourage it. Or maybe you want to just try for a few minutes on your own and see if what you get equals what somebody else got.
Wait, no, it's okay. What would you write?
Okay, I'm hearing a little more interaction now. You getting there? We want the pH close to 3. pH is close to 3. 3 point something, close.
Oh,
Does your arrow look like mine? Is it a one direction arrow or an equilibrium? Anytime you add a strong acid or base to a reaction, it's going all the way. You got to pick that up. So yeah, that's what we have here. We've got a weak acid. This is not a buffer solution. It's just a simple weak acid, and then a strong base gets thrown into it. So it goes all the way to the end until one of these runs out, and we're going to make water, and then the nitrite ion. So we're starting, since we're going all the way, we just need to do the stoichiometry in moles. 0.005 moles of hydroxide are added, 0.015 moles of bag. And we start with 0 bag. Water doesn't matter. I saw that. This is our limiting reagent that's going to all get used up, which is really nice, and I'll tell you why in a second, to 0. This goes down by the amount that went down to 0.010 moles. And then it goes up by the amount that went down to 0.005. Why is it nice that the hydroxide runs out first? What kind of solution are we left with? A buffer solution. It's a buffer solution. We have a weak acid present and some of its conjugate base present. So anytime you have a buffer, use the buffer equation to find the pH. And there's nothing wrong with finding the pH through the ice table, but man, is it handy to use the buffer equation. Recommended. So we're going to do this. pH equals the pKa, which is negative log of 4 times 10 to the negative 4th. And then plus log of base over acid, which is 0.005 over 0.01. 3.09, I think, is what you get. Anybody have any questions about that? Okay, good. So now we're a little bit warmed up, and you ready for me to punch you in the nose? Here it comes. This is probably the most commonly asked about question in all the homework. I think the solutions guide does a really bad job of explaining this, and that's why I get so many questions about it. So I thought I'd just go over this with everybody at once. Write down for yourself numbers 53 and 54 in the book. One of them you're assigned. Maybe, I don't think both, I think only one of them. But they all work similar to each other. Spend a few minutes on this one.